Okay, so so what we discussed last time. If b is less than 1, greater than 0, then limit b raised to n is 0. Right? This is what we discussed last time. Now, here for every epsilon, we can find k so that we can prove that limit is 0. But there are alternative ways also to prove this. Right. So, and what is that alternative way? So same idea, we can think about it in different way. So let xn be a sequence of real numbers Suppose xn is a sequence of real numbers. Suppose x is a real number, x is a real number, an is a sequence of non-negative such that limit of an is 0. So limit of an is 0. Third assumption, there exists C. C belongs to 0 to 1 means what? 0 less than C less than 1. And n, natural number n, such that the distance between xn and x is less than or equal to C times an for all n greater equal n. Then what can you say about limit of sequence xn? What can you say about limit of sequence xn? Can you guess? Yes. See, from this last expression, distance between xn and x is less than or equal to C times Cn. And what is given? Limit of an is 0. So ultimately, do you observe what will be the limit of xn minus x? Where this should go as n tends to infinity.
0.
0.
0. So this would go to 0. That means ultimately xn would go to what?
X.
X. So what we expect here now from this, then limit n tends to infinity xn is x. So this is what we can expect, right? And it is very easy to observe because we are assuming that limit of an is 0, and since this absolute value is non-negative, right? So absolute value is non-negative. Xn minus x is non-negative and it is less than or equal to c times an, right? And an tends to 0. By sandwich principle, xn minus x goes to 0 and ultimately xn goes to x. That is what we can observe. But let us try to prove this. And read the statement carefully again. Take 1 minute and read the statement. Everyone should read the statement carefully. What is a given data and what we want to prove? What is a given data? Xn is a sequence, x is a real number. Second point, an is a sequence of non-negative numbers, converges to 0. Third point, c is a number between 0 and 1. The main point is c is less than 1 and the xn minus x distance is less than or equal to c times an. Right? This is a given data. Okay, so what is our claim? What is given? First of all, list the data. An is greater equal 0 for all n because an is a sequence of non-negative numbers. Second point, c belongs to 0 and 1. That means c is less than 1 and xn minus x is less than or equal to c times an. After n, this particular n, this is going to happen, right? And what is our claim now? So limit of xn is x. So this is our claim. Means what is our what we should do now? What we should prove to prove that limit xn is x? What we should prove? That is what is our claim.
For any epsilon greater than 0, we
Correct.
can find out k.
So given any epsilon, we can produce k such that xn minus x is less than epsilon. Right, this is our ultimate aim. Once we are able to do this for every epsilon, we are done. And we can believe that limit of xn is x. Fine. And now look at the given data and what should be the strategy. What should be the strategy from given data to achieve this claim? What should be the strategy? Right, this is given. Therefore, xn minus x. So given, first of all, start with epsilon. Given epsilon, we'll start with epsilon. Given epsilon, we want what we want k. Is it clear? Given epsilon, we want k such that xn minus x less than epsilon after k. So this is our aim. But given data is k xn minus x is less equal c times an. After this n, right? This is true after x1, x2, and here it is xnth term. This is a particular term. After that, this is true. But if you want to make xn minus x less than epsilon, if c times an is less than epsilon, that is if an is less than what? an is less than what?
Epsilon upon c.
Epsilon by C.
Epsilon upon c. This should be. So if you want to make xn minus x less than epsilon, it is necessary to make an less than epsilon by c. And now is it possible to make an less than epsilon by c? Epsilon is already given, known, and c is also known given data. Is it possible to make an less
Yes,
than? Yes. Why?
limit of an is 0.
Right. Since limit of an is 0 for epsilon 1 is equal to epsilon by c, can I take epsilon 1 is equal to epsilon by c? Right? Because epsilon is already given now, known.
Yes, sir.
C is also known in given data, and this is positive quantity because both are positive. And limit of an is 0. So in particular for this epsilon 1, there exists k1, there exists k1 of limit an is 0 such that an minus 0 is less than epsilon 1 for all n greater equal k1. Am I right?
Yes, sir.
So what further? So what I can do further? Therefore, an minus 0 is just an is less than epsilon upon c. Epsilon is epsilon for all n greater equal k1. Right? But n are non-negative. Therefore, no need of absolute value sign. Correct? Right? Since ans are non-negative. So no need of absolute value sign because absolute value is same as an. Right. So now we can make an less than epsilon by c after k1. Now you tell me what is the required k? What is the what k I should select? What value of k I should select? I wanted to find k. What should be the value of k?
K1 itself.
But see, it is possible. See, after k1 it is possible, no doubt. After k1 an is less than epsilon by c. But that is possible if xn minus c less than c times an. When it is possible? When xn minus x less than c times an.
When n is greater than capital N.
So therefore, if both of the conditions satisfied, key an less than an is less than c by c epsilon by c, and xn minus x less than c times an. If both coincides, then we'll get that xn minus x less than epsilon. So what is the proper choice for k?
Maximum of K1 and N.
Right. So let k is equal to maximum of n and k1. Then is it the correct k? Let us check xn minus x. But see, when I say n is greater equal k, then ultimately n is greater equal n, right? Because I am choosing k is the maximum of n and k1, so k is greater equal n, and therefore ultimately small n is greater equal capital N. And if small n is greater equal capital N, this is less than or equal to c times an. Correct? Yes. Moreover, n is greater equal k and k is greater equal k1, therefore n is greater equal k1, and as soon as n is greater equal k1, an is less than epsilon by c, which is epsilon. That's what we get. Therefore, what?
Limit of Xn is.
Limit of, therefore xn minus x is less than epsilon for all n greater equal. Hence, for any epsilon, we are able to produce k. And what is the process to produce k? Right, process is find k1 and n1 is given, so choose maximum such that xn minus x is less than epsilon for all n greater equal k. Therefore, limit as n tends to infinity xn is x. limit of xn is x. So is it clear? Proof is clear?
Sir, but why is C compulsorily between 0 and 1? What if it is greater than 1? Still we can find an AN which is greater than epsilon by C.
No, not always. If your c is greater than 1, then it may happen that an converges to 0, but uh, so your sequence may not converge to x.
So can you repeat this in a short once again this proof?
See, what is given data? What is given data? An is a sequence of non-negative numbers, right? An is a sequence of
Yes, sir. Non.
non-negative numbers. C is a number between 0 and 1, right?
Yes,
And
sir.
xn minus x is less than or equal to c times an after some n, right?
Yes, sir.
And we want to prove that sequence xn converges to x. That means given epsilon, we want to produce k. Okay, so given that xn is less than or equal to c times n after n, but this xn minus x can be made less than epsilon if c times an can be made less than epsilon. And how is it possible to make an less than c times c by epsilon, right? So it is possible to make an less than c by epsilon because limit an is 0, and if you choose epsilon 1 as epsilon by c, epsilon is already given, c is known number, so choose epsilon 1 as uh, epsilon by c, right? Then there exists, because limit of an is 0, there exists some k, let us call it as k1, so that an minus 0 less than epsilon 1. That means, but an is are non-negative, so no need of absolute value sign. An is less than epsilon by c after k1. Right? If you choose k is maximum of n and k1, then after k, that means for all n greater equal k, xn minus c less equal c times an. That is true because n is greater equal n, and since n is greater equal k1, an is less than epsilon by c. So ultimately, xn minus c difference is less than epsilon. And so if you start with any epsilon, we are able to produce k depending on that epsilon, right? Hence,
Yes, sir.
hence we believe that for every epsilon we can produce k, hence limit of xn is x. Now we'll see some applications of this, right? So for example, if what I should say, a greater than 0, then limit a raised to 1 by n as n tends to infinity. What is this limit? So what do we expect? What is the limit? Right? For example, what is limit n tends to infinity 2 raised to 1 by n? Right? Or what is limit n tends to infinity 2 by 3 raised to 1 by n? So these are the questions which we cannot see directly where it is going as n increases. N is equal to 2, then in this case root 2, then 2 raised to 1 by 3, then 2 raised to 1 by 4, right? 2, then 2 raised to 1 by 2, then 2 raised to 1 by 3, then 2 raised to 1 by 4. So where it is going, right? That means if your a is greater than 0, what is a raised to 1 by n? A is a constant, right? And what is the limit? What we expect,
1.
right? So limit is 1. This is what we want to prove now. And therefore generally we believe that ki something raised to 0, a raised to 0 is 1. And what is the meaning of this? And this way I accepted easily ki something raised to 0 is 1, right? But this is true because of this, and here is the proof. Right. Okay, so we'll make cases. We proved it or not proved before?
हो सर.
Not proved. Okay, fine. If a is greater than 1, we'll make cases. Is, see, when I say a is positive means a is on this side, either a is less than 1 or greater than 1. So first case we assume that a is greater than 1. That means, for example, 2, 3 by 2, whatever. If a is greater than 1, then for natural number n, what can you say about a raised to 1 by n? Is it greater than 1? Yes.
Yes.
If you choose, if you choose any natural number and take nth root of a is greater than 1, then that nth root is also greater than 1. Why? Why? For all natural number, a raised to 1 by n is also greater than 1. Why? If a raised to 1 by n is less than 1, then if you take nth power less than 1 raised to n, means what? A is less than 1, contradiction. Because our basically we are choosing a greater than 1. Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
Therefore, therefore, if a is greater than 1, for any n, a raised to 1 by n is greater than 1. Fine. Therefore, a raised to 1 by n is some alpha n plus 1 for some alpha n positive. See, a raised to 1 by n is greater than 1 means what? A raised to 1 by n is greater than 1 means a raised to 1 by n is 1 plus something, and that is something is alpha n, right? So 1 plus alpha n is a raised to, right? Am I right? What I am saying is clear.
Yes, sir.
Yes, sir.
Yes, sir.
So this additional part, a raised to 1 by n is greater than 1 means it is 1 plus something. That additional part is alpha n, and that additional part is depending on n. For example, if a is equal to 2, then a raised to 1. That means n is equal to 1, which is 2, correct? But if you take
Yes.
n is equal to 2, then a raised to 1 by 2. That is 2 raised to 1 by 2 is square root of 2. Where is it? Do you see the where is uh, a raised to 1, that is 2 is here, correct? And if n is equal to 2, then 2 raised to half root 2 is here, right? N is equal to 3, then what is 2 raised to 1 by 3? It is still smaller, right? It is not same as root 2, right? 2 raised to 1 by 3 is not same as 2 raised to half. So therefore 1 plus something, that additional part depends on, this is alpha 2, this is alpha 3. So alpha n, what is the 1 plus alpha n? Alpha n depends on n, what is a raised to 1 by n. So is it clear?
Yes, sir.
Right. So that's why I am saying alpha n. It depends on what is n. If I look at a raised to 1 by 10, then it is 1 plus something alpha 10. But if I look at a raised to 1 by 11, then it is the additional part alpha is different than alpha 10. So alpha 11. That's why I am using suffix here. Fine. Therefore, if I take n power of both sides, so what will happen? A is equal to alpha n plus 1 raised to n. Correct?
Yes, sir.
Can I say that it is greater or equal 1 plus n times alpha n?
Yes, sir.
By which inequality?
Knowledge
Bernoulli's
inequality.
inequality.
Bernoulli's inequality. By Bernoulli's inequality, this is true for all n. Basically, this is true for all n. Right. Now, okay, further. So, therefore, uh, a minus 1 is greater or equal n times alpha n for all n. That means alpha n. Okay, let me mention here alpha n. Okay, alpha n is positive quantity. So alpha n is less than or equal to a minus 1 upon n, right?
Yes.
So alpha n is less equal a minus 1. Okay, I think I should anyway. Therefore, okay, what is a raised to? What is our a raised to 1 by n is alpha n plus 1. Fine. So what? So since a raised to 1 by n is since a raised to 1 by n is alpha n minus 1, what we have a raised to 1 by n minus 1 is alpha n. So this is 1, this is 2. So from 1 and 2, what we have? What we have? A raised to 1
A
by
raised to
n.
1 by n minus 1 less than or equal to a minus 1 upon n.
So a minus 1 into 1 by n, right? So this quantity is positive, a raised to 1 by n minus 1. Is it positive quantity?
Yes, sir.
Yes. And therefore, can I say that its absolute value is same as its?
So it should be a raised to 1 by n plus 1.
No, minus 1. ते सरांनी इथे चुकीचं लिहिलंय. अल्फा n प्लस 1 आहे वरती.
Alpha
Ah,
n plus. Here it should be alpha n. No, here minus, correct. Right? Is it correct now?
Yes, sir.
Okay, fine. Now compare with the previous theorem. Xn x c an. Is the situation similar? Actually, this is true for all n. Or you can say for n greater equal n. And you can say here capital N is 1. Is the situation similar?
Yes, sir.
Yes, sir.
And what is limit of an?
0.
0.
0. This is also satisfied. That means all the conditions. But from this, I notice one thing. I should make modification in the statement. Somebody notice it. It is not necessary that C should lies in between 0 and 1. Right? What is the requirement only?
That an should be limiting to 0.
The requirement is C is positive. Whatever is C. That means if you take C is equal to 1, then also no problem. That will be the more general and correct statement, right? Then you can make some modifications here also. Not necessary actually, C should be in 0, 1. Right, so C should be positive, that is sufficient. You correct it, no problem. Otherwise, then when I say A greater than 1, then A minus 1 is some positive number. If suppose A is 100, then no problem, right? But certainly this is positive. Is it true? C is positive. A minus 1 is positive. Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So therefore, by previous theorem, what can I say? Limit n tends to infinity, a raised to 1 by n is 1. Am I right?
Excuse me, sir.
Yes.
Yes, sir.
Sir, A
Yes,
minus
sir.
1 can be 0 also, no?
No, no, no. What is A? Look at the given our assumption. What is first case?
Okay.
We are choosing A strictly positive greater than 1,
Okay, sir.
not equal to 1. Right? So alternatively, you can look at it alternatively. So from equation 1, what is our expression 1? From 1, alpha n, right? What is the expression 1? A minus 1 less than or equal to A minus 1 upon n, right? By sandwich principle, what is limit of alpha n? What is limit of alpha n? What is sandwich principle?
0.
Right, so you can say this side is xn, this side is yn, this is zn, and zn converges to what? Zn converges to 0,
0.
xn converges to 0, and alpha n lies in between xn and zn, right? And therefore, where alpha n converges? Alpha n
0.
converges to 0, right? So by sandwich principle, alpha n converges to 0. Therefore, a raised to 1 by n is equal to 1 plus alpha n implies what is limit of a raised to 1 by n? What is it?
1.
Yes, 1, because alpha n by limit of sum is sum of limits. So this is alternative way, no problem. You can look at it in any way. Logic is logically, if it is clear, then you can look at it in different ways. Right? Correct?
Yes, sir.
So what is the next case? This is the first case if a is greater than 1. So case 2. Suppose what should be second case?
Lies between 0 and 1.
0 less than a less than 1. This is the second case. Then a raised to 1 by n is less than 1 for all n. Correct?
Yes, sir.
Right. That
Yes,
means
sir.
1 upon a raised to 1 by n is greater than 1. Right?
Yes, sir.
Inverse is greater than 1. Fine, then what we can do? So now this 1 upon a raised to 1 by n is greater than 1. Therefore, 1 upon a raised to 1 by n is some beta n plus 1. Am I right?
Yes, sir.
Yes, sir.
Correct. That means a raised to 1 by n is 1 upon beta n plus 1. So that I will take n power of both sides. Beta n plus 1 raised to n. Fine. Is it clear?
Yes, sir.
Okay. What we can do further? Because our ultimate aim is a raised to 1 by n tends to 1. This we want to prove. Right? It is sufficient to prove that beta n converges to 0 in this case also. But anyway, let us see what happens. By Bernoulli's inequality, what we have, beta n plus 1 is greater equal, raised to n is greater equal 1 plus n beta n. Right? Correct? Because Bernoulli's inequality is true for all. 1 plus x raised to n is greater equal 1 plus nx or x greater than minus 1. Right? If you remember. And here beta n is positive, so no doubt it is true. Bernoulli's inequality is true. Therefore, 1 upon beta n plus 1. Okay, let us call this as 1, expression 1. 1 upon beta n raised beta n plus 1 raised to n is less than or equal to 1 plus 1 upon 1 plus n beta n. Right?
Yes, sir.
Okay, then what we can do further? Okay, now is it less than 1 upon n beta n?
Yes, sir.
Yes. Okay, let us call it as 2. Right, then from 1 and 2. From 1 and 2. From 1 and 2, what one says, a is equal to 1 upon 1 plus beta n raised to n. But by second, it is less than or equal to 1 upon n beta n. Right? So, what should be my next step? Beta n is less than or equal to what? What? Beta n
1
is
by
less 1 upon a times 1 by n. And is it true for all natural numbers? No restriction on n. For every time this is going to happen. Correct? Yes.
yes, sir.
1 by a is constant for all n. And therefore by sandwich principle, what is limit of beta n?
0.
0.
0.
Fine. And therefore, what is limit of either you can say 1 upon a raised to 1 by n is limit of beta n plus 1. But what is right hand side now?
1.
1. And so ultimately limit of 1 upon something, that is 1 upon limit of a raised to 1 by n is 1, or ultimately limit of a raised to 1 by n is 1. Or you can use previous theorem also, you can make adjustments and then a raised to 1 by n minus 1 and so on. That kind of adjustment is also possible, but in any way limit is 1. Right. So the both of the proofs clear.
Yes, sir.
That's what we have proved. If a is greater than 0, then limit as n tends to infinity a raised to 1 by n is always 1. And this limit is very important and interesting. Now limit n raised to 1 by n. What is the limit? This is again very important limit and interesting also. What is it?
Sir, 1.
So this limit is also 1, but how to prove it? Let's try to prove this. So for n is greater equal 1, n raised to 1 by n is greater equal 1. Is it correct?
Yes, sir.
Yes, sir.
Right. Therefore, n raised to 1 by n is some gamma n plus 1, and gamma n is positive quantity because n raised to 1 by n is greater equal 1. So it is 1 plus something. So gamma n is greater equal 0. But if n is greater than 1, that means n is strictly greater than 1, then n raised to 1 by n is strictly greater than 1 for all n. Right. If n is strictly greater than 1, then n raised to 1 by n is strictly greater than 1, and therefore n raised to 1 by n is equal to gamma n plus 1, and here gamma n is positive quantity, strictly positive quantity. So is it clear what I am saying?
Yes, sir.
Okay. Now so n raised to 1 by n is gamma n plus 1, so that n is gamma n plus 1 raised to n. Right. Now let us expand this binomial expansion. What is binomial expansion of gamma n plus 1? 1. If I am correct, if I am making mistake, please tell me. N into gamma n plus n into n minus 1 upon 2 factorial gamma n square and so on, and last term is what? Gamma n raised to n. Is it correct?
Yes, sir.
Yes, sir.
Right. Okay, so therefore n minus 1, I will subtract 1 n from both sides, so n gamma n plus n into n minus 1 upon 2 factorial and so on, gamma n raised to n. Now on right hand side there are many terms. If I delete some terms, what will happen? and which term I am going to delete. Can I say that this is greater or equal n into n minus 1 upon 2 factorial gamma n square? So I will delete this term and all remaining terms. The resulting expression is smaller now, correct?
Yes, sir.
Yes, sir.
But I can delete these terms provided my n is greater or equal to, because then only I have some more terms and I can look at, I will get square terms provided my, in binomial expansion, if n is at least 2, then I will get the square term, right? Correct?
Yes, sir.
But and we can put this restriction n greater equal to, because we are interested in limit as n tends to infinity. That means we are interested in larger n. So we are not interested in smaller n, because we are interested in what is the limit as n tends to infinity. So this restriction is certainly we can put n greater equal to, and so we have this inequality. Fine. That means n into n minus 1 upon 2 factorial into gamma n square is less than or equal to n minus 1 for n greater equal to, for all n greater equal to. Right? Can I say that gamma n square is less than or equal to 2 upon n? Am I right?
Yes, sir.
Yes.
Yes.
Because n minus 1 I can cancel, no problem. Because I am choosing n strictly greater than 1. So it is non-zero quantity in any way. That's why I put the restriction n greater than 1 means n greater equal to. So that I can cancel n minus 1. If n is equal to 1, then it is not possible to cancel. 0 by 0 doesn't make sense, right? Therefore, whatever we are writing, everything makes sense. Key, the conditions are very essential. Anyway, so if I take square root, gamma n is less than or equal to root 2 upon n for all n greater equal to, and gamma n is non-negative quantity. So by sandwich principle, what is limit of gamma n?
0.
0.
Limit of gamma n is 0 because limit of 1 by root n is 0. And root 2 is a constant and 1 upon root n limit is 0. So by sandwich principle, both n goes to 0. So limit of gamma n is 0. Therefore, what is limit as n tends to infinity? N raised to 1 by n is limit as n tends to infinity 1 plus gamma n. And what is it?
1.
1. Right. Thus, we have proved very interesting thing. Key limit n raised to 1 by n is 1 as n tends to infinity. Now, so now let us prove what we did yesterday. If 0 less than b less than 1, then limit n tends to infinity b raised to n is 0. Using the previous theorem or previous criteria, can you prove it without epsilon k definition? How will you prove it without using epsilon k definition?
Sir,
By
if
using
we
the above method,
By
by the method that you used before, like assuming an alpha and like
huh,
that.
b is less than 1, so 1 by b is greater
Yes.
than,
Greater than 1. Yeah.
right?
Yes.
And for 1 by b raised to n,
Mm.
what is 1 by b raised to n?
Greater than 1 is
greater
2.
than, right?
Yes.
uh, and then therefore 1 by b raised to n is some alpha n plus 1,
Yes.
right? That means b raised to n is 1 upon alpha n plus 1, correct?
Now
And
taking
this,
the nth root. And by applying Bernoulli's inequality, we can prove that alpha n converges to 0. And then,
yeah, yeah, actually alpha n converges to, no, we want to prove that b raised to n tends to 0,
oh, yeah, yeah, yeah.
right? So therefore b is equal to 1 upon alpha n plus 1. Okay, alpha n is positive actually. This is 1 by n, but then there is a problem anyway. Okay, 1 by b is greater than 1, so alternatively just look at 1 by b is greater than 1, therefore 1 by b is some a plus 1 for some a greater than 0, right? I am looking at an alternative point of view, so b is 1 upon a plus 1, right? Therefore b raised to n is 1 upon a plus 1 raised to n, and by Bernoulli's inequality this is less than or equal to 1 upon 1 plus na, right? So this gives us something. Can I say that this is less than or equal to 1 upon n times c?
Yes,
Yes.
sir.
Yes, very good. And therefore now b raised to n is a non-negative quantity, right? Right? And by sandwich principle, what is it? A is constant basically. B is constant, so A is constant, right?
Yes.
Can I say this by sandwich principle? What is limit of b raised to n? 0, right? So alternatively, what I can see here is b raised to n is non-negative quantity. So I can say that b raised to n is actually same as b raised to n minus 0. Basically, it is non-negative quantity. And then compare with the previous theorem. Can you compare with the previous theorem? Yes. Is it possible to compare with the previous theorem?
Yes, sir.
So what is the situation here? X raised to n and x, here c, and here an. Limit of an is 0, c is positive because a is positive, and this is less than this. So this is a situation, right? So therefore we can say that limit as n tends to infinity b raised to n is 0. So here, without using epsilon and k definition also we can prove it by other technique. But here this is not going to help us. Uh, anyway, this is not going to help us, right? This part is not needed actually here. Okay, is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Right. Okay, now there is something. Let A belongs to R be a fixed number, right? Then what can you say about limit as n tends to infinity a raised to n upon n factorial? A raised to n upon n factorial.
0.
How can you see this limit is 0? Yes. How to prove this? So you think about it, how to prove this. Next time we'll discuss and we'll try to generalize this thing. We'll try to split this problem into simple cases and we can look at the general a raised to n upon n factorial. Right, so number is
Sir, it
complex.
should converge to 1, right?
It converges to
1, right?
no. It converges to 0, it is true.
Okay.
But how to do this? How to believe that it converges to 0? Because as when I am saying a is a real number, that means a can be greater than 1. Right, suppose a is equal to 10, then a raised to n, that is 10 raised to n. This going towards infinity as n tends to infinity, and denominator is also going towards infinity. Therefore, it is not. But if a is less than 1, then certainly a raised to n goes to 0. In that case, the job is easy, right? But still, that is difficult to believe if something tends to 0 and another thing is denominator going towards infinity. Then what happens? Then it tends to 0. That is clear, or you can understand it, right? So you think about it. Any doubt? We'll discuss this next time.